I am Deck Cadet Floro P. Casas III. I'm going to discuss the limitations or factors affecting performance radar and ARPA. So, first is the frequency. Frequency are the other way of measure of waves motions which indicates the numbers of crease that pass of fixed initial time. So, let's talk about what is crease. So, crease is the point on a wave with the maximum value of upward displacement within a cycle. A crease is a point on a surface wave where the displacements of the medium it is an maximum. So sa higher frequency, doon na siya sa per second niya has 14 cycle. So and sa low frequency has 4 cycle per second. So ang ingon diri kung higher frequency, kung greater siya sa attenuation, makakuha siya loss powers sa regardless lang sa weather. Ug sa lower frequency, di ba, ang sa lower frequency kas has 4 cycle pero iya 4 cycles. So pero iyang kuan siya about hinay siya pero ang yan cycle kaupat. So maningon na longer wavelengths og di. So this are the examples of high frequency wave and the low frequency wave. Second is the peak power. The peak power of the radar, it is useful power range capabilities of the radar increase with peak power. Doubling the peak power increase the range capabilities by about 25%. So ang peak power kay maximum na siya sa power level of the pulse ug multiplied na siya sa pulse width. Ug however kung meters used to measure by power in radar, so system so do over a period of time that is longer than the pulse width. So sa pulse, third is the pulse length. The longer the pulse length, the greater is the range capability of the radar because of the greater amount of energy transmitted. So ang pulse length kay usually called na siya na pulse width sa radar system. The pulse interval or the time from the beginning of a pulse to the beginning of the next kay determine na siya sa number of pulses na transmitted in a given period of time in radar. We measure all time in seconds or fractured of seconds. Ngayon na, the longer pulse width, the greater is the range capability of the radar. Is the pulse repetition rate. The pulse repetition rate or PRR determines the maximum measurable range of the radar. Ample time must be allowed between pulses for an echo to return from any target located within the maximum workable range of the system. Otherwise, echoes returning from the more distant targets still blocked by succeeding transmitted pulses. This necessary time interval determines the highest PRR that can be used. The PRR must be high enough, however, that sufficient pulses hit the target and enough echoes are returned by the radar. The maximum measurable range can be determined by approximately by dividing 81,000 by the PRR. So, one example sa pulse length. So, ang pulse length kay na siya nasa center og sa center og sa pinakadulo sa beam width to measure the pulse length. So we have the beam width. The more concentrated that be, the greater is the detection the detection range of the radar. So ang beamwidth sa radar kay antenna na is usually understood to mean the half power of beamwidth. The angular distance between the half power points is defined as the beamwidth. Oh, as we can see, mao na siya ang example sa beamwidth. Ang ingon, the angular distance between the half points is defined as the beamwidth. So there is the spacing shorter than pulse length equals 1 echo. Spacing greater than the pulse length 2 echo. So we can makita na ito echo. Yeah, the horizontal beam. Last is the receiver sensitivity. So ang receiver sensitivity, the more sensitive receivers provide greater detection ranges but are more subject to jamming. So as ato may bawaan kay ang receiver sensitive, from the word sensitive is the levels that tell us the weakest signal that a receiver. Sensitivity describes the weakest signal's power level that the receiver is able to detect and decode. So it depends on the lower signal to noise ratio at which the signal can be recovered. Different modulations and coding schemes have different minimum SNRs. Sensitivity is determined by adding the required signal to noise ratio to present at the receiver. Ang source ani kay the thermal noise and noise introduced by the receivers, the pre-amplifier. So that's all. Thank you.
I'm Pedro Albarracin. So describe the IMO performance standards for ARPA. First is detection, where a separate facility is provided for detection of targets other than by the radar observer. It should have a performance not inferior to that which could have been obtained by the use of the radar display. Second is target acquisition. Target acquisition may be manual or automatic for relative speeds up to 100 knots. However, there should always be a facility to provide for manual acquisition and cancellation. ARPA with automatic acquisition should have facility to suppress acquisition in certain areas. On any ranges scale, acquisition is suppressed over a certain area, and our area of acquisition should have defined and indicate on display. When we say suppressed, it means a suppressed means as area set by the observer within the targets are not acquired. And then automatic or manual acquisition should have a performance not inferior to that which could have been obtained by the user of the radar display. When we say acquisition, it means the process of selecting a target and initiating their tracking. Next is tracking. Tracking is the ARPA should be able automatically to track, process, simultaneously display, and continuously update the information on at least 20 targets, whether automatically or manually acquired. So when we say tracking means that computer or process observing the sequential changes in the position of a target in order to establish its motion. So tracking also, the ARPA should continue to track acquired to target which is clearly distinguishable on display for 5 out of 10 consecutive scans, provided the target is not subject to the target swap. So the possibility of tracking errors, including the target swap, should be minimized by the ARPA design. A qualitative description of effects of error sources of automatic tracking and corresponding errors should be provided to the user, including the effects of low signal to noise and low signal to clutter ratios caused by sea turns, rain, snow, low clouds, and non-synchronous emissions. Next is display. So the display may be a separate integral part of the ship's radar. However, the ARPA display should include all the data required to be provided by the radar display in accordance with the performance standards for navigational radar equipment. So design should be such that malfunction of ARPA parts producing the data additional to information to provided by the radar as required by performance standard for navigational equipment should not affect the integrity of the basic radar presentation. So ARPA also facilitates should be available on at least 3 to 6 and 12 nautical mile range scales, and there should be a positive indication of a range scale in use. So ARPA should be capable of operating a relative motion display of north up and course up, course up azimuth stabilization. In addition, the ARPA may also provide for the true motion display. True motion display is if a true motion is provided, the operator should be able to select for that display either true or relative motion. There should be a positive indication also of the display mode and orientation in use. The course and speed information generated by the ARPA for acquired targets should be displayed in a vector graphic from which clearly indicates the target's predicted motion with relevant symbol in this regard. So when we say north up and course up, north up is a display means of azimuth stabilized display in which line connecting to the center and with the top of the display is north true bearing. So course up is a display means azimuth stabilized display in which line connecting to the center with the top of display is own ship's intended course. And also azimuth stabilized means a display which is azimuth orientation relative to nominated true bearing is fixed. Next is operational warnings. So the ARPA should have a capability to warn the observer with visual and audible signal of any distinguishable target which closes to the range transits of a zone by chosen by the observer. The target causing warning should be clearly indicated with the relevant symbol on display. The ARPA should have capability to warn the observer with the visual or audible signal of any track target which is predicted to close with a minimum range at time chosen by the observer. The ARPA should also clearly indicate if a track is lost other than out of range, and target's last track position should be clearly indicated on display. So it should be possible for the observer to activate or deactivate the audible warning signal. Next is data requirements. So the observer should be able to select any target with the obtained data. Targets selected should be marked with the relevant symbol on the radar display. If data required for more than one target at the same time, symbol should be separately identified, for example with number 1 adjacent of the symbol. So here are the following data for each selected target should be clearly and unambiguously identified and displayed immediately and simultaneously in alphanumeric form outside the radar area. First is the present range of the target. Second is present bearing of a target. Third is predicted target range at the closest points of approach, or CPA. And 4 is predicted time to CPA. Then fifth is calculated true course of the target, and 6 is calculated true speed of a target. So trial maneuver. The ARPA should be capable simulating the effect of an all targets of ownership maneuver without time delay. Before maneuver, without interrupting the updating of the target, and display of actual target's alphanumeric data. The simulation should be indicated with the relevant symbol on display. The operational manual should be contain an explanation of the principles underlying the trial maneuver technique adopted, including, if provided, the simulation of own ships maneuvering characteristics. So when we say trial maneuver is a facility to assist the observers in making the correct maneuver for navigation and collision avoidance process. Next is accuracy. So what is accuracy? Is monitor the proper operation of the system. Additionally, test the programs should be available so that the overall performance of the ARPA can be assessed periodically against a known solution. When test program is being executed, the relevant test symbol should be displayed. Next is sea and ground stabilization. The ARPA should be capable of a sea and ground stabilization. Lag and speed indicators providing inputs to the ARPA equipment should be capable of providing the ship's speed through the water in the fore and aft direction. The ground unstabilized input may be provided from the log from the electronic position, fixing if the speed measurement accuracy is in accordance with the requirements, or resolution from track stationary targets. The type of input and stabilization is in should be displayed. So when we say ground and when we say sea stabilization, it is a display wherein own ships and all targets are referenced. All targets are referenced to the sea using the gyro heading and single axis log water speed inputs. When we say also ground stabilization is a mode of display wherein the own ships and all targets are referenced to the ground using ground track or set and drips input. So that's all, sir.
Hello everyone. This is the procedure on how to set up radar ARPA display system. So basically, before we start into the controls of the radar, it is important that we know how marine radar operate and some of the terms associated with the operation of the radar. First is go to 12-mile scale and make it sure that it is X-band. Then click transmit and come down, make it sure that in manual, and then adjust the tune to lower bar. Then adjust the gain. To do that, I'm going to make it sure that my sea and rain are down. Now I'm going to gradually bring this up. Looking at the screen, I begin to see that there is yellow spot, and I want to turn this up enough so that there's yellow spots all the way to the edge, and adjust to make this clear. Next is make it relative motion, which I am. Then click north up, which we are on our example. Then turn on the trail. Then down here to tools and start to mark the original position of the targets. Click add and drop a circle on the targets like this, and also you can delete it like this. Then after on, that's ready. It is ready. So that are the procedures on how to set up a radar display system. So if you need more, I have a video. So come on, let's watch this video to understand more.
Okay, so in this video, I'm just going to run you through the basic steps that you're going to have to do every time we start a new simulation in the radar lab. Okay, so I'm going to run you through that. So first thing we're going to do is you may as well just go ahead and put yourself on 12-mile range, because that's the range we're going to want to be on. The manufacturer says for this radar that you want to be on 12 to 24 when you're adjusting the gain. We're not going to do the gain just yet, but we might as well just go ahead and put us on 12, and that's probably what you're going to want to be on anyway for the simulation. So that's the first thing. The other thing is we're going to go ahead, we're going to put this on X band right away. When it comes up, it may come up automatically on S band. We want to be on X. To do that, what I'm doing is that you'll have a mouse, and I just right-clicked. When I right-click, I just toggle between X and S. We'll talk more about the difference between X and X later, but you want to be in X band, okay? Let's not worry about the master right now. Then you're going to come down here to transmit, okay? And you're going to click on transmit. Now, when you click on transmit, the first thing we're going to do is tune. Right now we're in manual, and if I click that, I can put it into automatic, okay, frequency control. But this is the radar doing its own thing, and you know, you probably when you're working, you'll let the radar tune itself under many conditions, but not all. But we want you to learn how to do it, so I want you to make sure it's in manual, and you're going to want this to be in manual as well. We want you to have to tune the radars in the lab so that we can sign you off on being competent to do that. Later on in the future, you can use the automatic features, but right now you should be using manual. So the first thing we're going to do is adjust the tune right here. And by the way, I'm moving the cursor on the table there. So first thing I'm going to do is I'm going to, you can see there's the box, by the way, next to the cursor. The left box is turned white and the right box is empty. That means that if I left click, I can do something. So I'm going to left click here. Those are my tuning bars. Now, for this radar, when you want to get the best tune, what you want to do is you want to get that lower bar as long as you possibly can. So it's right about there. And once I do that, I just click and it's set. Okay? So now the tune is done. Next thing I'm going to do is I'm going to adjust the gain. Now, this is where the manufacturer says you should be on 12 to 24 mile scale, okay? So we're already on 12. Now, to do that, I want to make rain and sea. We'll explain what these are in greater detail in the future, but for right now, this is how you set up the radar at the beginning of every simulation. And in some labs, you'll be doing 2, maybe even 3 simulations. So you'll have to do this every time we put you, in a new situation. But anyway, you want to turn the rain all the way down. So I clicked on it. Now I'm dragging my mouse to the left to make the bar go down to 0. And I'm going to do the same thing for C. Okay? Now, this gain is, the name from this comes from how this technology used to be organized in the past. Now it's really known as threshold. But basically what you're going to do is you're going to left click on that. Now what we're doing is we're adjusting the sensitivity, the threshold of the receiver, okay? So this is happening on the receiving side of the radar. And right now you can see here, if you look around, all right, there's a few targets on the radar, but what we're going to do is we're going to adjust the threshold, okay, where right now what I'm doing is I'm actually increasing the sensitivity, and what that's doing is it's making the weaker targets are going to have more of an effect on the screen. So by the way, if I jack this all the way up, I'm going to have what's called saturation. And saturation is where every bit of energy that's coming back, or in this case, most of the energy that's coming back is actually showing up on the radar screen. This could be waves, this could even be birds and stuff like that. Now, if we had a weak target like a wood vessel, we might not be able to pick it out. I can see right now that there are 5 targets on this thing. So, but if I had weak targets, I wouldn't be able to see them and all that yellow stuff. So I want to bring it back, but I don't want to bring it so it's so low that now look, no targets are showing up. The threshold is set so high, the sensitivity is essentially so low, is so high that not even the strongest targets are showing up. So I got to have some middle ground. And here's how you figure that out. You bring this up nice and gradually. And if you look at the screen, you'll see that particularly in the middle, right at the very middle of the screen, you see there's those little yellow dots. You might call those snow or something like that. And I'm going to bring the gain up until I get some snow pretty much over the entire screen. I just want a light speckling of snow all the way out to the edge of the screen. And by doing this, what I'm giving myself confidence in is that I'm going to be able to detect weak targets, okay, far out, okay? But I don't want it to be like this, okay? So I just want a few speckles going out to the outer edge of the screen. Okay, now you may not be able to see these in this video, but I'm just, okay, that's probably just about there, okay? But the problem here, now I'm going to click. The problem here now is that, you see, I got a few little speckles out here. That's good, but my goodness, I've got a ton of speckles in the middle. That's what we're going to use rain and sea for. We're going to speak about these, the time constants. We're going to talk about these in much greater detail, particularly in the lecture. But right now, I'm just going to show you how you can use them. So most of my speckles are around the middle. And so if I have most of my trouble just around the middle, I'm going to use C. And I turn the C on, and I just bring that up a little bit. Now, as you see, as I gradually bring that up, you can see that the radius, you see that the speckles are disappearing, and the radius of that circle is getting bigger and bigger as I bring C up and up. Well, essentially what I'm doing is I am reducing the sensitivity inside that little circle. And the more I bring it up, the more I can knock down those waves. But also, if I had a weak target in there, I'd also knock that down. So this is a bit of a compromise as well. Okay, so I would probably set that to around here-ish or so. And then, I have some light speckles everywhere. What I might do is I might just put, this is just a touch of rain, okay? And I think I've got a pretty well-tuned screen right now, okay? I still have a few little speckles, but now I can see my 5 targets, okay? So, that's pretty good. Okay, so that's done. Now the next thing I'm going to do is I'm going to turn on a few little features. So you might want to put your range rings on, okay? For a 12-mile scale, it's telling me that each one of these is 2. So that's 2, 4, 6, 8, 10, 12. By the way, the scale is the radius from the center, okay? So the next thing I'm going to do is I'm going to start to set up my modes. So I'm going to come over here to this side now, and I have, you can see that looking to the right of the cursor, those 2 boxes just turned white. That means I have right click and left click options. Okay. So what I want to do is I want this to be in relative motion relative. And to do that, I right clicked, and we'll talk more about what these are. There's relative motion, relative motion, true, and true motion. We're going to talk about these quite a bit in the lecture, and you'll experiment about with them somewhat in the lab, but you should, for the labs, put it relative motion relative. So RM parentheses R. Okay, so that's done. The next thing we're going to do is we're going to set our orientation mode. So again, we're going to talk much more about this. This is just a setup video here, but you want to be, for these labs, we suggest you be in north up. Okay. Now you didn't really see much of a change right now. That's because the vessel is actually heading north at the moment. Okay, which I can tell because here's the heading right here. This is like a gyro here. This is our heading. This is our speed. Okay, or log W. We'll worry about all that stuff later on. But this vessel is heading north, and now this is north up. Anyway, good stuff. All right, we'll talk much more about that later. Now, vectors, we're not going to worry about vectors at all until we get into ARPA. You can see ARPA error right now. That's going to be the case. You're going to have ARPA error until about lab week 10 when we start to play with the ARPAs and you start to learn about them. I said play, but it's really not playing. This is a very serious tool. So So you're going to have ARPA error for a few weeks. So these vectors aren't going to matter until we start to let you use the ARPA. But you're probably going to want to turn your trails on. So you click on that, and there's short, long, and permanent. In practice, you'll probably be using short or long, but for when you're actually working, short or long. But for your first lab, maybe we'll have you put it on permanent so that you can see the entire history of motion. That will make sense to you later on. Turn it on, turn your trails on. It's a very useful tool. Okay, now, another thing that you might do is put marks on. So if you're going to put marks on, you're going to go down to Tools, okay? And then you're going to go to Add, okay? So you click the tool, you go to Add. And when I go to Add, what I'm going to do is I'm going to come up to my targets. Now, by the way, these targets, there's 5 targets on here. I'm going to turn my range rings off. There's 5 targets on here. Okay. Now we have to come up with some nomenclature for how we're going to number these things. Like you might call this target 1. I might call this target 3. Somebody else might call this target 5. Might call this target 2, 1, 2, 3, 4, 5. Anyway, it could be any random numbers. And if we're in here in the lab and there's 8 students and 1 instructor and an assistant, that's 10 people. We have to have a consistent nomenclature. So here's what we're going to do. This white line right here is called the heading line, or the heading line, okay? And that is indicating the direction the vessel is heading relative to this orientation mode. Okay, by the way, I can suppress the heading line over here by pressing on that. You see it goes away. And I might want to do that if there was a target along that heading line that might be obscured by it, okay? But anyway, there it is. So we're going to take the orientation of that, and then we're going to start to go clockwise, not counterclockwise. We're going to go in a clockwise circle, and whatever target we come to first, in a clockwise circle will be target 1. So this is target 1. That makes this target 2. That makes this target 3. That makes this target 4. That makes this target 5. Okay. So if I want to put marks on these now, which you probably will, I'm going to go to Tools. I'm going to go to Add. And then what I can do is I can come right up onto the target and I put a mark, and you see a little circle gets there. And if I want to add another, I'll put, and so you're probably going to be doing this, we'll probably have you doing this at least at first, as a useful way for you to mark the original positions of the vessels when the simulation starts. Okay? And here I am, I'm marking all 5 of my targets. Great. Okay, if I want to delete one, let's, I put that in the wrong spot. Like, let's say I thought I put that one in the wrong spot. I go delete, and I take it off. I can also delete all. Okay, but anyway, there you go. Add. Okay, this is target 1, 2, 3, 4.
So this is Leo Lucero, and I'm going to demonstrate the setting up of ARPA display, system performance, operational test and warnings, and target information. Radars on board are probably the most used equipment during navigation. It is a good tool for the lookout. We are so much dependent on the radar that sometimes we use it more than we use our eyes for lookout. Before we start into the controls of the radar, it is important that we know how marine radars operate and some of the terms associated with the operation of radar. Radio wave. A radio wave is transmitted and received back by the scanner. The time is calculated between transmission and receiving back this wave. The speed of the radio wave is known, and thus the receiver unit calculates the distance of the target. After processing, it displays this information on the display's screen. The rotating scanner also calculates the bearing of the target and displays on the radar screen. There are a couple of terms related to radar that we need to cover before we proceed further. These are radar resolution and radar sensitivity. Radar resolution is the ability of the radar to show 2 targets which are close to each other as separate targets on radar. There are 2 types of radar resolution: range resolution and bearing resolution. Range resolution means radar can paint two close targets as separate ones. Range resolution depends upon pulse length. For bearing resolution means radar can paint two near targets on same bearing as separate ones. For sensitivity or radar sensitivity, in simple words, sensitivity of radar is how thick a radar plots the targets. A better sensitivity means a radar can paint even a fishing boat a slightly bigger target. Less sensitivity means there are chances of a fishing boat missing on the radar screen. Now that we know these terms, let's see how best we can set a radar to display the targets perfectly. For gain, see and rain. Gain. Gain is used to increase the receiving sensitivity of the radar. It needs to be adjusted to a level where targets are visible but there is no other interference on the screen. C. C control to reduce the clutter echo caused due to surface of the sea. Rain. Rain control to reduce the clutter echo caused by rain. And now let's play a short video for gain, sea and rain.
When you first arrive in the simulator, the radar will be set up in the standby mode. What we first need to do is to tune the radar to give us the best possible picture in the prevailing conditions. What I ensure first is that we have sufficient range so that when we set the gain, we will have sufficient gain for all the ranges that we are using. I now go down to Transmit, as this is where I access my gain, tune and anti-sea clutter controls. I make sure that I zero the controls so that I can start from a clean slate. I increase the gain, and I'm increasing the gain till I get a speckled background, and then I'm just removing it so that the screen is clear. I then tune the radar. This radar has an auto-tune function and I use that. What I can do now is I can go down to the range at which I will be navigating and then use any anti-clutter controls. As you can see, there is quite a bit of sea clutter present. I'm going to use the anti-sea clutter control to remove some of that clutter. I am careful not to use too much anti-clutter control, as I will definitely affect targets. That looks about right. At the moment, my radar is in the ship's head-up mode. I may right or left click and put it into the north up mode. What I do is I check that the heading displayed by the radar is the same as that displayed by my gyro. Our heading is in degrees true.